You haven't shared the screen, right? Hello? Federico? Hello? Hello? I didn't hear you. Not sure. Hello, Federico? You haven't shared the screen.
Oh, no, not yet. No, I think I lost my connection for a moment. Hopefully it's going to be all right. Sure, shall we try the...
Please, I was asking you to share earlier.
Okay.
Okay,
Seems
great.
to be working well.
Yeah, let me press recording. Welcome everyone to Harvard CMSA Quantum Matter in Math and Physics seminar. We are delighted to have Federico Bonetti from Durham University. He will be speaking about non-invertible symmetries from holography and branes. Let me remind the audience, please feel free to interact with Federico and ask questions. Let's directly welcome Federico. So yours, please.
Thank you. Thank you very much for having me. It's a pleasure, and really thankful for this opportunity to tell you something about this work on mine in collaboration with Fabio Pruzzi, Ibrahim Abba, and Sakura Shepard-Nameki. I would like to start with some introductory remarks, and in particular, about non-invertible symmetries in field theory. In the past few years, we have witnessed a dramatic generalization of the concept of global symmetry in quantum field theory. And the central idea that moves forward these interesting generalizations is that we should think of global symmetries as being implemented by topological operators, and they can have various dimensions in our space-time. This is a very vast and interesting field of research, but one of the most exciting developments that we have seen quite recently is the study of global symmetries that are non-invertible. So to be a little more precise, here I'm referring to the case in which the symmetries are implemented by topological operators, but when we consider the fusion of two of these operators, as in this schematic diagram, in general, we can get not just a single term, but a sum of terms. So a fusion that it's not based on group multiplication. And in particular, it happens that some simple objects fail to have an inverse, and that's where the name non-invertible comes from. Now, while these symmetries were quite well established in dimensions 3 and lower, finding them in dimensions 4 and higher was a genuine surprise. And it has prompted a lot of interesting recent progress that it's still ongoing today. And for instance, while these symmetries might appear a little exotic or unfamiliar at first, they do appear in many familiar examples of four-dimensional field theories. They can appear in pure Yang-Mills, or they can also appear in massless limits of, say, QED or QCD. And it has already been demonstrated how they can have very interesting dynamical implications. For example, they can be used to think about the Payan Lagrangian in QCD. And also, we have witnessed some early phenomenological applications. This is probably just the tip of the iceberg. There have been some ideas related, for example, to the problem of neutrino masses in beyond the standard model physics. So this is a very exciting and active area of research. And we can, of course, think about these problems within field theory. But what I would like to do today is use a slightly different point of view, and in particular, trying to see whether we can use string theory and holography as a way of learning something new about these non-invertible symmetries. And I would like to give you a few motivations why this can be interesting. First, we can remind ourselves of the fact that if we use string theory and holography, we can access regimes of quantum field theory that would be challenging to study otherwise. For instance, holography helps us understand some aspects of strong coupling regime of field theories. Or another remarkable fact is that string theory predicts the existence of non-trivial fixed points in 5D and 6D. Those are strongly coupled theories, and they have very interesting and non-trivial reductions, for instance, down to 4 dimensions, that are also generically strongly coupled. Moreover, this is maybe a little more philosophical, if you wish. When we think about QFT in string theory or holography, usually the data that defines our model is topological or geometric in nature. We have to describe the kind of string background or brane configuration we are considering. And personally, I find this sort of very satisfying because it's aligned very well to a more modern topological and geometric point of view on symmetries that we see on the field theory side. And more pragmatically, there are many aspects, especially of non-invertible symmetries, that might be hard to study in some cases in field theory. Sometimes fusion can be challenging, for instance. So we might hope that a different and complementary approach based on string theory and holography can tell us something new, or can give us new ideas how to think about properties of non-invertible operators. And this line of research is relatively new, but there are already a few works out there. And so this is quite a broad set of questions. Let's consider something a bit more specific. We would like to make inroads into this program. So let's select a quantum field theory that we have under reasonable control. And the model I would like to study today is for the n equals 1 super Yang-Mills, and in particular with gauge group SUM. This is a quite non-trivial field theory that, for instance, exhibits confinement, but it's still amenable to be studied holographically within the framework of Type IIB string theory, building on the seminal work of Klebanov-Strassler. And in particular, as I will review later, this 4-dimensional theory has appropriate discrete global symmetries, 0 form and 1 form. And here, just to remind you of the terminology, 0 form is just an ordinary one. 1 form means that it acts on lines generated by codimension 2 topological operators. And importantly, these symmetries have a mixed anomaly. And indeed, if we gauge the one from symmetry, on the one hand, we are describing, again, a for Dn equals 1 super Yang-Mills gauge theory, but now the gauge group is PSUM. And more surprisingly, the 0 form becomes non-invertible, as this was the construction of this very nice paper. So given that this model has a holographic dual that we can handle and exhibits the non-invertibles, the question we would like to address today is, how can we see the non-invertible symmetry in the dual supergravity description? Is it possible? And the answer is affirmative. And before giving you the derivation, I would like to give you a summary of the main results that we have found. So on the one side, we can detect the non-invertible symmetries from the supergravity bulk action. So this would be a 5D supergravity action. In particular, it turns out that if you analyze this supergravity action, you will find a non-trivial set of topological couplings among various p-form fields. And importantly, these topological couplings encode the symmetry data as well as the Toft anomalies of the dual field theory in 4 dimensions, to the point that actually this is the same data as the symmetry TFT. This is a concept I will review in a bit more detail later, but it's essentially an auxiliary theory that lives in 5D and precisely captures data about the symmetries and anomalies. Building on this, we have a systematic way of finding symmetry generators, including also non-invertible ones. To do so, we build on work of Witten and Belov and Moore and others, considering a Hamiltonian quantization of this 5-dimensional action, where we treat the radial coordinate of our holography as Euclidean time. This is in this cartoon on the right. What we can do is to consider the Gauss law constraints that we find in this 5-dimensional theory. And those are also the generators of gauge transformations in 5D. Once those are identified, we can consider the case where they are brought all the way to the holographic boundary. This is also schematically depicted in this picture. And we will see that then, depending on the choice of boundary conditions in our theory, these Gauss law constraints can yield either invertible or non-invertible symmetry generators. So in other words, the bulk action knows precisely about this new and exciting kind of symmetries that we would like to understand better. If you wish, we can think of this almost as a bottom-up approach. We need the data of the 5D bulk supergravity, but we can also ask ourselves whether we can use some of the objects of the full 10-dimensional construction to understand better what is going on. And this is the second part of our results, and namely how indeed we can use D-branes for that purpose. Yes?
A question, maybe the previous slide?
Of course.
Just make sure the relation between the Gauss laws, they enclose some surface or some extent operators, right? And the relation of that, the extent operators, is that related to the symmetry generator in one lower dimension simply through projection or what? Can you explain a bit more about this?
Sure, we will also see this in greater detail. Essentially, we'll see how we can construct the Gauss law constraints by picking a fixed slice, a spatial slice, which is the same as a radial slice. So they live at a fixed value of that coordinate. And then they have some extended directions. And in particular, to describe a zero-form symmetry, we need 3 extended directions that are in the directions of the holographic boundary. So we consider this as at a fixed value of the radial coordinate, and we effectively consider a limit at which this value of the radial coordinate becomes larger and larger as we approach the holographic boundary. So this in particular is not extended, as you can see, along the radial direction. It's just at a fixed radius. And then we tune that value of the radius. That's one way to think about it. I hope this helps to clarify.
Would you be more, yeah, that helps, but would you be giving some explicit examples maybe later?
Oh, no, sure, absolutely. This is just sort of an appetizer if you wish, but then I would like to give you a more thorough derivation of all these facts, absolutely. And then, indeed, sort of to wrap up the appetizer, so to say, I would like to say something about the D-brane part of the story. So what we will see is that we can indeed realize the symmetry generators in terms of D5 branes that we have in our 10-dimensional setting. And very much in very close analogy with the previous slide, these branes are going to be at some fixed position in our radial coordinate, and they will be partially wrapped in the internal space-time, leaving 3 directions in our 4D directions of where our QFT live, the dual QFT. And what we will see that makes the whole construction sort of make sense is that the action of the this wrapped D5 brane becomes topological in the limit in which it goes to the boundary. And the topological terms are such that it precisely correspond to the field theory construction of Kaidi, Omori, and Zhang. And furthermore, we will see how the dynamics of the branes sheds light on some properties of the non-invertible symmetry generators. So in particular, thanks to the Myers effect, we will be able to understand an example of fusion rule of non-invertible generators. And instead, we're using Alani-Witten transitions. We will see how these non-invertible symmetry generators act on some line operators that we have in our theory. So I find it personally very rewarding that these well-known and well-established dynamical effects on the D-branes are precisely what's needed to capture interest in physics of the non-invertible generators on the field theory side. So there is a very nice correspondence. And again, I'll be able to tell you later in greater detail how all of this works out. So having given a little motivation and an appetizer of the results that are about to be discussed, for the rest of this talk, I would like first to give you a brief review of the field theory construction. So why exactly in this theory we have non-invertibles. I'll then briefly describe the holographically dual setup in Type IIB. And building on this, we will be able to then see the derivation of the two parts of the story that I have briefly alluded before. And after that, I'll come to some conclusions and point out some possible future directions. So if there are no further questions about the introduction, I would like to proceed with a review of the construction of non-invertibles on the field theory side. So the model of interest for today's talk is indeed for Dn equals 1 super Yang-Mills. And let's have a look at some of the discrete global symmetries that this field theory exhibits. The first ingredient we need is a discrete zero-form symmetry. So this is an ordinary symmetry, and we can think about it as a remnant of the classical U1R symmetry that we would see in the Lagrangian of this model. Because of the ABJ anomaly, which involves two SUM gauge fields, as in the famous triangle diagram depicted there, this U1 is broken down to a Z2M. And since this is a global symmetry, we can couple it to a background field. And since it is discrete, we think of the background field as a cohomology class with coefficients in Z2M. Here and in the following, W4 is going to be our spacetime where our 4D theory lives. The second ingredient is a one-form symmetry. This is a ZM, and it's nothing but the center symmetry of SUM gauge group. So the charged objects in this case are lines, the Wilson lines. And since this is another global symmetry, we can indeed couple it to a different background field. And this time it's going to be a degree 2 class because it's a one-form symmetry. And finally, in a sense, the most important ingredient, a mixed Toft anomaly between these two, which can be captured in a compact way by this expression, which is something of degree 5 on an auxiliary space whose boundary is our spacetime. And here, well, A1 and B2 are precisely the background fields introduced before, and P is the Pointeragian square operation. Okay, so these are the three ingredients to keep in mind. Now let's see what their interplay is. And in order to do that, I would like to first start with a very simple observation. I mentioned we have this zero-form symmetry, which is a Z2M. And essentially, by definition, that means that our theory has codimension 1 topological defects. So I'm going to note them D3, since we're in 4D space-time. And they are labeled by elements of the group Z2M. And their fusion rules are group-like. So this is really nothing surprising. There is, though, something a little more interesting going on. In fact, due to the anomaly, the ABB anomaly that we have in our 4D theory, the topological defects D3 are themselves not gauge invariant if we perform a gauge transformation of the B2 background field. As an example of something that is indeed gauge invariant, we can instead consider this combination written down here. But as you can see, I am using an auxiliary form manifold and this Pointryagin of B2 quantity to make it gauge invariant. Now, it is important, though, to emphasize that the fact that D3 is not gauge invariant does not mean that it's not well-defined or genuine operator, because B2 is just a classical C number. It's just a background field. So at this stage, we have a perfectly well-defined, invertible, usual zero-form symmetry. Now, the interesting things start to happen when we gauge the one-form symmetry. So that is a very standard operation in the realm of discrete symmetries. It means that we, and as usual, we promote the background field, B2, to something dynamical. And here I'm going to use a lowercase notation to emphasize that. And since the original one-form symmetry was related to the center of SUM, we know that the theory after the gauging is with gauge theory PSUM. And as it's well known, this has a magnetic one-form symmetry. We can think of this as a quantum symmetry that comes out of the gauging. And it is generated by the holonomies of B2. These are topological surfaces. And we'll see these objects appear momentarily in other equations. And here comes the most interesting part of the story. Now the D3 operator indeed is no longer well-defined because it's not gauge invariant and we are gauging the one-form symmetry. And the lesson of this KOZ paper is that we can fix it if we stack it with a suitable 3D TQFT in such a way that this TQFT has an anomaly which is precisely opposite of that of D3, so that together they're anomaly free and they can exist in the gauged theory. While the choice of TQFT is non-unique, there is a well-defined notion of minimal choice, which is usually denoted with this AM(1) notation. In the present context, this is the same as U1 level M transimus theory in 3D. And therefore, we are led to defining an improved version of the D3 operator, which is D3 stacked with AM1. And now this object is indeed topological and completely well-defined. And in the genuine operator supported on a three-dimensional manifold M3. So we have succeeded in rescuing the zero-form symmetry from being destroyed, but this has now become non-invertible. And one way to see this is to have a look at a couple of fusion rules of these curly N defects, the new improved versions. As a first example, I would like to consider what happens if we take the defect itself and its conjugate. In this case, it has been demonstrated that on the right-hand side of the fusion, naively, we would get the identity if this was a group-like fusion. Here we get instead a condensation defect, which we can think of as a mesh, if you wish, of D2 surfaces inserted inside our M3 where the N defect lives. So this is a quite dramatic example of a fusion rule that it's definitely not consisting of a single term on the right-hand side. And another interesting example is what happens if we take the defect and we make a fusion with itself. In that case, we can describe what comes out of the fusion as the naive defect of charge 2. So that would be the naive group-like part. But then this will be stacked with an abelian TQFT, which is essentially the UM from each factor on the left-hand side. Indeed, if M is odd, we can be much more precise because one can demonstrate that this U1 times U1 TFT factorizes. And the factorization is into a product of two minimal theories, AM2, so that the fusion rule takes the form that is depicted there. So we have an N2, that's the improved version of the D2 defect with the minimal dressing AM(2), whereas the other copy of the AM2 survives as a TFT coefficient in front of the fusion rules. So that's yet another example of a fusion rule that is much richer than the ones that would appear in a more traditional group-like symmetry. So these are two examples of the non-invertible nature, and we will see, we will try to now understand the features of this field theory properties from a supergravity and holographic point of view. So if there are no questions about the review of the field theory part, I would now like to switch gears and tell you something about the holographic setup that we will consider. And as I mentioned in the introduction, we will be considering the Klebanov-Strassler setup in Type IIB, which is closely related to for Dn equals 1. So we don't need to consider the Klebanov-Strassler solution in full detail, but it's useful to keep track of the two main ingredients that are really important for us. In a first step, we can imagine taking D-branes at the tip of the conifold, which is the Calabi-Yau cone over T11, this Sasaki-Einstein 5 manifold. And we don't need to know very much about the geometry of T11 for this talk. I would just like to remind you that topologically, it's just a product of a two-sphere and a three-sphere. Now, if we were to stop here, this would be a CFT. And the dual, of course, would be ADS5 times T11. The other crucial ingredient are now D5 branes that wrap the S2. So they look like fractional D3 branes, if you wish. And they have a back reaction that modifies the solution in interesting ways. We will be interested mostly in the large radius regime, so that captured by the Klebanov-Strassler solution. And here I gave you sort of a few equations. We don't have to go through all of them in a lot of detail, but I would like to emphasize a few features. The first is that while we no longer have an ADS5 metric, there is still a notion, of course, of radial holographic coordinate, and the slices at constant r are still Minkowski. That's not surprising. And the other feature that will be very important later that I want to emphasize are the m units of F3 flux on the three sphere. We will see that these are quite important for our discussion. So this is the supergravity solution we have in mind and we would like to use. And let's remind ourselves briefly of what's happening on the field theory side of this holographic correspondence. On the field theory side, we have a gauge theory with a product gauge group with these ranks as indicated, as well as bifundamental matter. And indeed, what happens when we follow the RG flow is that one of these gauge factors becomes strongly coupled, and it's best studied by performing a Seiberg duality, which then is going to change the rank of the gauge groups. And then the same is going to happen to the other factor of the gauge group. And the whole thing goes on, and it's usually referred to as a duality cascade. And we can see here schematically how the various ranks of the gauge groups are changing along the process. From this cascade, we also see that if we choose in particular n to be a multiple, an integer multiple of m, and that's what we are implicitly doing for the rest of the talk, we expect the duality cascade to terminate on pure SU and super Young-Mills. So in this sense, this holographic setup is related to the field theory that we would like to study. And while the cascade is quite, like there is a lot of physics going on, it is interesting and sort of reassuring to observe the following simple statements that are though important for us. Namely that at each step of this cascade, we can see all the three main ingredients we need in our symmetry analysis, and namely the correct zero-form symmetry, the correct one-form symmetry, as well as the mixed anomaly that's really the crucial ingredient of the field theory construction. So in other words, we have a candidate, a very well-controlled holographic setup to investigate. Is there any question? Okay. So having given this brief review on the holographic setup, we can now go to the derivation of the facts that I mentioned briefly in the introduction, so that we'll be able to clarify better how we got there and what all those results mean. And the first part of the story will be how we can extract non-invertible symmetries from the bulk supergravity. Before doing that, I would like to say a few words on the symmetry TFT. So this is a picture that has emerged, and the content of this is the following. What we would like to do is to study, say, the global symmetries and anomalies of a theory, say, in 4 dimensions, for instance. What we can do is to study an auxiliary theory, a topological field theory that lives in 5D, and that admits the theory that we want to study as a boundary condition. So this would be what I'm denoting as relative QFT, the red line. This is not necessarily topological. At the same time, however, this symmetry theory also admits a gapped interface to an invertible field theory. And would be the green theory in the diagram. And that's the anomaly theory. If there are no anomalies, that would be just nothing, and the gapped interface would be a gapped boundary. And the idea is that if we imagine to squeeze the gapped interface onto the relative QFT, then we would get a absolute QFT, which is potentially anomalous. And in particular, the choice of gapped interface corresponds to choice of global structures. And what we would leverage for the rest of the talk is this in this box. Namely, what we want to do is to characterize our symmetry and anomalies from a holographic perspective. And the strategy we'll be using is to essentially observe that we can extract the symmetry field theory if we look at the topological couplings of the supergravity action. So those will be the main focus of the remainder of this section. So that's our goal. We have our task. We have the system, and we want to study. But before jumping to the detailed analysis of the Klebanov-Strassler story, which has a lot of moving parts, I thought it would be useful to remind ourselves briefly of this relation between holography and the SymTFT in a simpler setting, and namely n equals 4 super-units with clearly dual radius 5 times this pi. In this case, we know that the topological couplings of the 5D bulk action include a BF kind of coupling between two forms with level M. And we also know that we can consider different topological boundary conditions for this BF theory, and they precisely correspond to various choices of global structure in the spirit of the, say, reading between the lines paper, for instance. And of course, depending on the value of M, there are there could be many possible boundary conditions. It's quite rich structure. Let's have a look, though, at 2 simple examples, because we will sort of see their analogs in the Klebanov-Strassler story. One of the simplest things we can do is to recover the SUM gauge group. To do so, we declare B2 to have Dirichlet boundary conditions, whereas C2 is freely varying at the bound. The fundamental strings that are charged under B2 can now end on our holographic boundary and become Wilson lines, whereas the holonomies of C2, the guy that has free boundary conditions, we can consider them at some radial direction, and in the limit where we push them to the boundary, they become topological operators that implement the one-form symmetry under which the Wilson line is charged. So all of this in this cartoon here. And then the other example I want to mention briefly, it's simply the S-dual picture. This time we use Dirichlet on C2 and free boundary conditions on B2. The D1 brane ends and becomes a Toft line, whereas the holonomies of B2 become the generator of the symmetry. So I'll be brief because, as you can see, it's clearly the same in a dual frame, so to say. So this was a reminder of this connection And we will see essentially a slightly more involved version of the same ideas.
By the way, excuse me, Federico.
Sure. Yes.
When you earlier say topological boundary condition here, do you say many? Here you only provide two, right? Just the b equal to 0 or c equal to 0, right?
Oh, not true. That I'm not exhausting all possibilities.
But you say there are many?
Yes.
I want to confirm the way you define those boundary conditions. Just make sure.
Sure, absolutely. So, for instance, one generalization we can consider of the two examples that are shown here would be one where on the PSU side, instead of taking the Dirichlet boundary conditions for C2, I first define a linear combination like C2 plus an integer B2, and then impose the Dirichlet boundary condition on that, leaving B2 free. And that would correspond to turning a discrete theta angle in the language of the reading between the lines paper, for instance. So here I have denoted this PSUM theory with this 0 because I was thinking of the simpler case where that discrete theta angle is turned off. So for instance, this gives us more examples of this. To get even more examples, for instance, sometimes the integer m can be factoring the product of two integers. If that's the case, for instance, we can choose the Dirichlet boundary conditions for, if you wish, a subgroup of Zm related to this factorization of the integer, and whereas other boundary conditions for the other factor. So we can play with the factorization of m, and that gives us even a richer set of boundary conditions. And maybe to be a little more precise, here I'm referring more generally to gapped interfaces to invertible theories, by which I mean that, especially in these examples where we factorize n, it might happen that the field theory has both electric and magnetic global symmetries, and they exhibit a mixed Tofte-norm. So I'm okay with that case. I would like to consider it on the same footing as these other simpler situations. But to be more precise, that correspond in this other picture I draw earlier to this general situation where the CMTFT admits a gapped interface onto an invertible theory.
Sure, thanks. But let me make sure some of the boundary condition by choosing like b equal to 0, b2 equal to 0, c2 equal to 0, indeed will give gap topological boundary condition. How do you know other choices they are topological and gapped? Especially you say there could be theta angle for the corresponding gauge theory on the boundary. How do we know those are topological and gapped?
Well, but indeed, let me mention that in general, it's clearly indeed a non-trivial problem to identify all topological boundary conditions. In the present case, the topological nature can be seen because of the topological nature, of course, of the bulk action, and also how the boundary conditions are prescribed. We have made no reference whatsoever, say, to a conformal structure on the boundary, or, for example, or we don't need to fix that or any other non-topological data. So those are, if you wish, a specification of an action and boundary conditions that are manifestly diffeomorphic invariant. So in that sense, I think we can argue that they're indeed topological. We don't require any additional structure.
One thing I usually will think of is that suppose you specify some, let's say, Dirichlet boundary conditions, say some of the field b plus kc equal to 0. Those means those operators can end, right, on a boundary.
Yes, that's right.
And then you can check. You may need, there could be even more additional condition you can set other than this one. It depends on the theory, and then you can check the lines that, or sorry, the operators from the bulk extend from the bulk and on the boundary, and compute the link invariant by just consider arbitrary configurations of the bulk operator. When they form some non-trivial link, then you can check the path integral with this link insertion, and that means checking the statistics of the braiding process of those operators. And if those are trivial statistics, means that partition function does not give any complex phase, then you can define consistent gap boundary condition. But I wonder whether this is the same way you think about this gap boundary, or
I think indeed the picture you're drawing is also, it also applies here, because we can also precisely think of what sort of holonomies of B2 and C2 in the 5D theory indeed have trivial correlation functions. That corresponds to selecting effectively a maximal set of operators that are mutually commuting. And so indeed, it's another way to think about these topological boundary conditions. So it definitely corresponds to what you have pointed out.
Mm-hmm. But it seems like you are choosing this boundary condition as some kind of a gauge theory. And how do you know this also corresponds to gap phase of a gauge theory? Maybe this is something I was asking earlier.
I'm thinking of the, are you referring to the theory that lives on the holographic boundary?
Yes.
So
you are considering confined gap phase or certain phase of the gauge theory?
Well, here I'm more thinking, if you wish, let me go back to the other picture. So I think that would be, that in a sense refers to the red line. It's this not necessarily topological theory, it could be a gauge theory that can do various things in the IR. But here I'm thinking on the other side. So in a sense, I'm trying, one of the advantages of the SymTFT point of view is precisely trying to decouple this sort of problem. So we have indeed non-trivial field theories that are not necessarily topological, and but we can try to study aspects of their global symmetries looking at the purely topological side of the story. So in that sense, that's what I have in mind here. We're given a TQFT in 5D, and we are playing a topological game. I'm not here addressing directly the question whether or not this 5D TFT admits, say, a gauge theory as a 4D boundary. That's not what I'm trying to do here.
Okay, just last time, make sure. So when you say example SUM or PSUM gauge theory layer, are you specifying the gap interface or the relative QFT actually?
So in reference to this, thank you for the question. Let me clarify this point. In reference to this picture, so the red line, the relative QFT, we can think of it as gauge theory with algebra SUM, if you wish. Per se, it's not quite an absolute theory yet. We haven't chosen a maximally neutrally local set of line operators. Now we choose, say, Dirichlet boundary conditions for B2 on the green line, the gapped interface. So the choice that we make on that side, if we imagine to squeeze the sandwich in the SymTFT story, would correspond to selecting the global form SUM of the gauge group, so that we no longer have just a gauge algebra, we have a gauge group, and we have chosen a set of line operators in our 4D theory. So I was using the labels SU and PSU in this sense. Like that would be the gauge theory that you get when you close the sandwich from this point of view. Yes.
So when you say SUM or PSUM and with a sublabel 0, just one sentence, which interface are you specifying?
So I'm considering the topological side of the story, the green line, when I say, for instance, that C2 has Dirichlet boundary conditions and B2 is freely varying. That's a choice that I can do in the 5D topological theory, and it corresponds to gauge group PSU without any additional discrete theta angles, hence the 0 as a notation device. So in that sense, that's the correspondence I have in mind, which will.
In this picture, is the blue region? Do you mean to specify relative QFT or not really? The blue region is a relative QFT. This region.
I see. Well, it turns into. Well, as you can see, since we are choosing, this is more in a sort of holographic context, if you wish. In one case, for example, we find the Wilson line. In the other case, we find the Toft line. So when I'm talking about the Wilson line, I'm thinking of an absolute SUM, for instance. And when I'm talking about a Toft line, it would be the absolute PSU.
I don't think you answered my question. I was asking whether the ink correspondent, just this the slide you show right now, you have this blue region. Is that blue region correspondent to the relative QFT picture in the previous slide?
So isn't it like when you have collapsed the gap boundary and the relative QFT? So it's like I think it's like maybe I'm wrong, Federico, but isn't this like the theory that you obtain once you collapse the gap boundary and the relative theory for the different gap boundaries that you could have chosen?
Is a blue region a gap boundary or relative QFT? Is a blue region a gap boundary or is a relative QFT?
In this picture, I'm not thinking about it as a gap boundary. I want to think about it as, indeed, say, a gauge theory. So I can see in this sense how the holographic picture is related to, but it's not identical to the SymTFT sandwich, that it's a purely field theoretical construction. So in that sense, I'm sorry, maybe that was a little misleading. What I'm thinking here, if you wish a bit more precisely, we can say that the supergravity action has this topological coupling, and it has one derivative. So at long lengths, at long distances, it dominates the discussion. And therefore, holographically, we can consider the problem of finding boundary conditions for this, with the idea that those will correspond in the dual field theory to a choice of global structure. Yes, I'm not here. The blue region is supposed to be the field theory, the dual field theory, which is not necessarily topological.
But is it a relative QFT? The blue region.
It's not, because we have chosen boundary conditions such that we have chosen a maximal set of lines that are mutually local. It's once we do this, once we make this choice, the green region, it doesn't suffer from potential problems that relative field theories might suffer from.
Yeah, I'm still didn't get it. I'm familiar with each of the context, but I didn't know how do you put this together. Sorry, just didn't get it. How is this picture compared with the previous slide? Are you meant to say the things that cut as a dashed line? There's another interface. Is that that's not a? Is that a gap interface you want to specify? Not really. The dash, there's a dash slice, right?
Oh, no. Sorry, no, that's not supposed to be. It's just supposed to indicate that something has some fixed radius, as opposed to extending along the radial direction. That's all I wanted to emphasize with the picture.
And that's related to this quantization picture of Hamiltonian picture that you want to map the Gauss law to.
Indeed, in a moment we will become we will use the radial direction as time, as I mentioned, precisely.
Okay.
Okay, so
I
yes.
still just didn't see you answer my question. Is the blue region a gap interface or relative QFT or what? What exactly is a blue region? How do you define the blue region? Just by the boundary condition you specify there. But you say it's not necessarily gap. Is that right? The blue region. Do you get?
The blue region represents the holographically dual theory in 4D, which is indeed not. It would be a gauge theory in this example. And here I'm referring to this standard picture by which the BF term in the holographic, in the supergravity action dominates at long distances. The holographic boundary is sort of infinitely far away. So the bulk action becomes that. And then if you wish, it becomes an ingredient of the ADS-CFT correspondence in order to pinpoint not merely a gauge algebra, but a gauge group for the dual theory in 4D. On the gravity side of the story, we have to consider this topological coupling together with a choice of boundary conditions, topological boundary conditions for this coupling. So I can see maybe how this diagrams might be a little confusing because I'm maybe conflating what's happening on the dual field theory in contrast with what's happening purely in the supergravity description. But I thought it's sort of like a visual device to establish this correspondence between, say, for instance, when a fundamental string extending in the radial direction in the supergravity description becomes dual to a Wilson line in the dual 4D field theory.
Okay, thank you. Thank you.
Yes. No, thank you for the clarifications. Indeed. So, so it was important, I think, to address these points in this simpler setting, because what we will see now is a more involved version, but in a sense with similar ingredients. So if we go back to Klebanov-Strassler, the point that we have to find is to find the topological couplings, the analog of this B2, DC2. They're going to be a little more involved. And then indeed proceed with the quantization, or rather the Hamiltonian analysis and the Gauss-Log constraints. As far as the first step is concerned, the technical details are not maybe super important, but I would like
Federico,
to.
One question.
Yes,
So,
sure.
sorry.
Absolutely.
So then the claim is not. I mean, it's not that supergravity gives you the SymTFT, right? So,
Well,
is the claim that supergravity is the SymTFT of the holographic dual, or is it not that, or is something else the claim?
The claim is that the symmetry TFT can be extracted by considering the topological couplings of the supergravity action.
Okay, thanks.
Thank you. Okay, so how do we get these topological couplings? There are various ways of doing it, but I would like to point out a way that it's quite systematic and also helps with gauge invariance along the way. And the idea is to use an auxiliary 11 form that captures the topological couplings of type IIB. And it's written here, and in terms of the F3 and H3 fluxes, as well as the, thanks to this E5, which is, as you can see, closely related to the self-dual 5-1 flux. So this is building on some body of work of mine and my collaborators. We have studied objects like this in theory and type IIB. And their purpose in this instance is to encode not only the standard cubic coupling that we see in the action, but also the self-duality of F5, which is sort of a subtle aspect of the formulation of the theory in 10D. And it imprints itself onto the set of topological couplings when we do a reduction. And let me mention that this idea of using a Chern-Simons in a higher dimensional to describe self-dual P-forms is actually very general and has been used successfully in the literature. So this would be our device to perform the computation efficiently. And then the computation proceeds. There is a technology that my collaborators and I have developed. We don't need to go into the full details, but at least I can show you and give you a flavor of the sort of objects we find. So in the box here, we find our starting point, the auxiliary 11 form and the Bianchis of type IIB, the Bianchi identities. When we go down, we get a whole collection of field strengths. There are all these H3, F3, and etc. Not super important right now to keep track of all of them, but good to know that we have a few. And the physics of these objects is encoded in two pieces of information. The first are the Bianchi identities that we have now in 5D. We're going down in dimensions. And as you can see, we find two non-trivial ones, the first two. And then there is another auxiliary form, which captures the topological couplings we have downstairs. So how is this supergravity story related to the field theory story? We can see there is a very precise correspondence, actually. For example, the first Stuckerberg coupling is responsible for turning a would-be continuous U1 into something that's actually discrete. That matches with the discrete zero form that we have on the field theory side. And in a very similar way, the other Stuckerberg, also in combination with this H3F3 term, this is nothing but a BF coupling with one extra derivative to make it into a 6 form. Together, they give a GCD kind of discretization, which is also good news because that's the one form that we have in the for general values of n and m. And then, as I mentioned, for us, n will be a multiple of m, so this just becomes Zm. And then finally, what about the third ingredient, the mixed anomaly? That's what these two terms are doing. They are a continuum description of the ABB anomaly that we see in field theory. So overall, we see that there is very precise dictionary between what we see in field theory in the language of discrete symmetries and anomalies and the continuous p-form fields of supergravity. So it's rewarding to see how the supergravity language can encode all the data that we need in this sort of neat way. So having described the couplings in this more synthetic language of I6, now we can unpack them and actually get a 5D action, which is what we are actually interested in. To this end, there are a couple of technical points, not super important, but I would like to mention them. The first is to solve the Bianchi identities, that it's completely standard. The only thing I'd like to mention is that we will be working with globally defined potentials. So to do so, we have to write a contribution. I'm going to use the letter B. That's the cohomologically non-trivial part of a closed form. So for instance, let's look for definiteness as this expression for G2. So the Bianchis tell us that G2 minus MB2 is going to be a closed form. And here I'm writing it as an exact piece plus something non-trivial in cohomology. So it's a fairly standard decomposition. And the other little technical thing we have to do is to dualize the C0 potential into a C3 potential. And when the dust settles, we land on our desired topological couplings. And here they are reported for completeness. The most interesting ingredient is the very last one. This is, again, another manifestation of the mixed anomaly that really drives all the interesting things that happen in this setup. And now here I'm focusing on the topological couplings. Clearly, the full bulk action contains all sorts of other terms, including kinetic terms for these fields. And everything can also be derived, an alternative point of view, from the consistent truncation studied by Cassani and Faedo, as well as by the analysis that was done in this other paper. So now we have the good starting point, and we can proceed. This is, if you wish, the analog of the B2C2 we saw in n equals 4 super Yang-Mills, and clearly it's more involved because we are trying to study a system that exhibits more intricate phenomena. The philosophy, though, as I mentioned at this point a couple of times, is simply to consider the radial direction to be time. Everything will be decomposed into things that have legs along the radial, that don't have legs along the radial direction, or things that do. Here, I'm writing dt because we're really thinking of it as Euclidean time. And And now comes an important, it's elementary, but it's important observation that in the 5D action, we don't find time derivatives of the temporal components of the gauge field. So those instead are Lagrange multipliers, and they implement the Gauss law constraints, which are themselves generators of gauge transformations. So this is completely standard material. I was just thinking we can very briefly remind ourselves of how it works in a very familiar example of Maxwell theory. Clearly it's a very simple example. We have our familiar action. In this case, the momentum conjugate to the space part of the gauge potential is simply the electric field, and the Gauss law is literally the divergence of E being zero. There is a canonical Poisson bracket that I'm writing here in this form, and what we can do is we can take the Gauss law, so divergence of E, dress it with any function chi, integrate, and we get a functional f. And this functional, through this Poisson bracket, has this action as reported. And as we can see, this is literally a translation of A by gradient of chi. So in other words, this is the very precise sense in which Gauss law constraints generate gauge transformations. So this was a very sort of simple reminder. The same applies to the more involved case that we're actually interested in studying. So without further ado, we can compute the Gauss law constraint for A1, and it takes the form reported here. It's a fourth form consisting of these two terms, plus something that comes from the kinetic terms, but I'm not writing it down explicitly. And now that we have this fourth form, we can integrate it on a domain M4 that has a boundary M3, something we can do. And applying Stokes' theorem to the first term, we turn it into an integral of just C3, whereas the second term remains an integral over M4. So this is the quantity that encodes the Gauss law constraints in the bulk. And everything now is at a fixed radial slice. Now so this is sort of depicted in this cartoon. This green blob is our domain M4 with its boundary. Everything lives at fixed radius for time. And now we slide this. We want to consider what happens as it goes towards the holographic boundary. Now, just like in n=4, the contribution of the kinetic terms can be neglected in this situation. But what really happens to this object that I'm calling O depends on the boundary conditions for the bulk fields, C3 and G2. And again, I'm not here, we haven't performed the classification of these, but we can consider two examples that are paradigmatic of the sort of physics we encounter. In the first case, we take our object and we imagine to let C3 fluctuate at the boundary. So we're not fixing it, but we do fix G2. We don't sum over G2. And if that's the case, the whole G2 part of this quantity is just a C number. We're not summing over it. And the interesting part is the holonomy of C3. So what we interpret this in terms of the dual field theory is that this is the SU theory that has invertible zero-form symmetries. And as you remember, the defect there had a 't Hooft anomaly, and that's essentially the same as this G2 square. So it's very rewarding to see how the Gauss law reproduces this feature on the nodes. And now, however, we can start from the very same object and consider simply a modification of the holographic boundary conditions and say that we do sum over G2, we let it fluctuate. If that's the case, we cannot clearly regard this G2 squared as a C number, and our task is a little harder. We have to find something, I'm calling it M3, such that when you raise it to the 2m power and you put it on something which is the boundary of M4, it gives us precisely this object. So if you wish, informally, we have two things that we have to do. Being able to divide by 2m and turn the integral over M4 into an integral over M3 only. And this is possible, but there is a price to pay. And that's introducing a new gauge field, A1, which is localized only on M3. And then, if we consider this Chern-Simons action, we realize we have the desired object. So in other words, what I'm doing here, as you can see, indicates that we are in the PSU case where we indeed find a non-invertible. The non-invertibility has the same origin as in field theory. It's due to this dressing by a non-trivial QFT, which in this instance is U1 level n. So in other words, to summarize, the very one object in the bulk, which is canonically defined and systematically extracted, is able to reproduce both invertible and non-invertible generators.
Federico, why
Sure.
did you? I mean, why do you know that this operator should? To the power of 2m should be 0?
Oh no, sorry, not 0. That's the notation. This is curly O, which is
Okay,
the
sorry,
same thing
yes.
that went up there. Sorry, that was me.
Right, sorry. And how do you know that?
Well, it's a way of phrasing. Morally speaking, we know that the symmetry generator should be the holonomy of C3. But as you can see, the Gauss law comes with this 2m prefactor. So morally, we would like to divide by 2m in the exponent, so take the 2mth root. And for the first term, of course, that's trivial. For the second term, it would sort of lead to something that we can regard as a inappropriately quantized transaminds. This is actually essentially the same idea of the fractional quantum Hall effect that is used to save the APJ anomalous chiral symmetry, for instance. It's the same idea. So this transaminds coupled to G2 gives a proper definition of what would be a 1/2m kind of transaminds.
Okay, thanks.
Thank you. Okay, so this was all I wanted to say about the supergravity part of the story. And so now we can switch gears and say something a little about the branes. So we'll see now how D-branes also give us an insight, can realize the physics of these non-invertibles. Actually, we don't have to start from scratch. Let's revisit what we have done in the Gauss law constraint analysis. So the main character was this holonomy of C3. But now, if we see the holonomy of C3, we are naturally led to think of something that couples electrically to C3, some sort of extended object in our 5-dimensional bulk. To identify what that is in terms of 10-dimensional objects, we can trace back the origin of the little C3 field in 5D. As you might remember, that guy started its life as being the dual of another field, C0. It so happens that C0 comes from the C2 field in type IIB on this 2-sphere. And clearly then by 10D electric magnetic duality, it means that little C3 originates from the C6 Ramon-Ramon potential in 10D on the 3-sphere. But this is enough to give us a clear indication of what kind of D-branes we should consider. They should be D5s, since they couple electrically to C6, and they should be wrappings S3. So this gives us 3 unwrapped directions, and those are going to be taken along some spatial slice. So as you can see, the picture is more or less the same. We have some radial fixed value, that's where our brain lives. So it extends parallel to the boundary and does not extend in the radial direction. So this is the proposal. We can use D5s of this sort to describe symmetry generators. Now we have to have closer look at what this proposal entails. And the first thing we can do is to consider the D-brane action. This contains in general the DBI term and topological West-Zubino couplings. We can think of the DBI terms as a generalized kinetic term, roughly speaking. It is governed by an effective tension, and it can be checked that as the brane goes to larger radial directions, that scales like r to the power 3. So that means that the DBI action is effectively frozen, and therefore the effective action becomes topological at large values of the radius, which is good news since we want to reproduce a topological generator of a symmetry. Of course, we have to now determine what kind of topological action we find, but this is a well-defined task.
So, Federico, can you explain why the tension scales as r to the cube? I would have expected some logarithmic dependence rather than cubic dependence from the volume of the CSV.
This can be seen from the, if you wish, in the DBI action, there is the square root of the determinant, and we can expand essentially do a derivative expansion in the scalar field that governs the transverse direction. And there is a square root of the determinant prefactor that comes without those fluctuations. And that can be verified to scale like that. So that's, in a sense, the origin of that. It can also be related to the, if you wish, it's the number of directions that are not wrapped, along which this object is extending parallel to the holographic boundary. So that could be seen as another source of this exponent.
Okay, thank you.
Thank you. Indeed, what are the topological terms? Well, they are well known in 10D. It's the famous West-Zumino action.
Let me add something really naive, just to make sure. So earlier, I guess you are trying to consider, two scenarios. One of the scenarios, the field theory has interpretation for 4D n=1 PSU1 super Young Mills that you have constructed a non-invertible zero-form symmetry, right? Symmetry generator, and I guess you are trying to produce the more familiar field theory result from maybe from supergravity or something. That part I'm not sure. I guess you already go through it, but I guess I don't have enough understanding to connect that. Can you say a few words, like, so the crucial part of this zero form symmetry, one form symmetry mixed anomaly, how it's descend from the high dimensional theory from somewhere? Can you make just some comments about this?
Sure.
Just say a few words. I guess you have a wave of this relation, but and they need to come up with those. But I guess right now I just want to hear by words. Those formula maybe may help, may not help. Just say by words how the zero form symmetry.
Well,
thanks.
I think maybe I just want to flash.
This one. Yes.
Yes, the object on the top. Yeah, I think so. That's what is that object? So we have taken the topological couplings in supergravity, and we applied this standard procedure of Gauss-Log constraints. And this is the outcome. So this is a four form. Well, this is not a four form. Rather, I'm referring to this object. Maybe this is really the starting point. And as you can see, it consists of two terms. So the first term would be there without the mixed anomaly. That's just simply to tell us that in the supergravity language, the zero-form symmetry generators are related to the holonomies of C3, which also makes a lot of sense intuitively speaking, just the dimensionalities work out well. This G-squared term is precisely the mixed anomaly. So the mixed anomaly gets imprinted in the Gauss-Log constraints through this coupling. It originates from the AGG. Essentially, we strip off an A. And as in a sense, this is, if you wish, something like an anomalous Gauss-Log constraint. It's the same. It knows that there is a mixed anomaly through this quadratic term, and the whole point is to deal with this extra term, because dealing with the first term, it's trivial. Clearly, we can just turn this into a holonomy of C3, and if we wish, we can remove the 2m coefficients by just simply dividing. So that's not the interesting part. The interesting part is what happens to G2 squared, which came from the anomaly. So here we are faced with a twofold task. We have to turn this into something that we can integrate on a three-dimensional manifold, because that's what the topological defect implementing the zero-form symmetry should be. And we want this object to start with a 1 in front of the C3 term, because we want to generate to capture the generator, so to say, of the of what would be the Z2M. And therefore, this is what we're faced with doing. And if we choose boundary conditions such that G2 is dynamical, this process is what gives us the non-invertible. Because then to make sense of these, to find C3 plus something else as an integral over a three-dimensional manifold, we have to produce this auxiliary gauge field, and we recover the dressing that also appears in the field theory discussion. So yeah, in a nutshell, the Gauss law knows about the anomaly, and it goes along for the ride until the very last minute, where we have to write the operator as holonomy of C3 dressed with something appropriately. And that's the non-trivial dressing that is responsible for the non-invertible nature.
Okay, thanks.
Thank you. Indeed. Let's see how the branes know about this.
Probably also, I guess that's also something probably just assume everyone know. But since this is a quantum matter seminar, let me just ask again. Let me ask something really naive. So in the end, in the full quantum gravity theory, all the whatever symmetry, generalized global symmetry, all are gone, right? There should not be any global symmetry. So in the sense, you have some realization of those non-invertible symmetry, maybe from high dimensional theory. And how should I think about those objects that you identify in the even full quantum gravity theory? Should they also be gauged and they disappear? Or just maybe should you comment about that as well?
Sure. No. I mean, so one, from the point of view of the supergravity action, I have focused on the topological terms, but there are, of course, many more terms, like the full dynamics involves everything, Zipline modes, stringy modes. So indeed, even if one might find some global symmetries maybe of that topological terms, that's not the focus here, because indeed, as you mentioned, eventually on supergravity side, we don't have any global symmetry. The point is, if you wish, that those are a gauge symmetry in the 5D bulk. That's what the Gauss law constraints tell us. They're generating gauge symmetries as opposed to global ones. And they're nonetheless, then holographically, they become global on the other side. And the same, in a sense, it's true with the D-brane picture. Like here, I'm thinking of a D-brane that effectively becomes topological because I would like to reproduce a symmetry generator. But in the deep of the bulk of the gravity theory, of course, the brane is very far from being topological. And there is, of course, all sorts of other states and excitations that would guarantee the absence of global symmetry, as we know should be the case.
Okay, thanks.
Thank you. Indeed. So let's see how the branes know about the field theory construction. It's actually relatively simple. This is the starting point, the topological couplings on a D5. We have to see what happens when we wrap it on a 3-sphere, and one can do the computation and actually recover exactly the field theory construction. In that, what happens is that we know that there is a U1 gauge field on the word volume of a D5. That's one of the really crucial features of the physics of D-branes. And here it fits perfectly with the field theory because it's precisely the localized gauge field on the word volume that is responsible for the U1 level M dressing. And in terms of supergravity, this comes precisely from this flux, M units of flux that become the level of the Chern-Simons theory. And now maybe I'll be brief because it's very analogous to the other story that we have seen in the Gauss law constraints. Now we have this topological term and we have to see what happens when we push it to the boundary. And here the idea is that A1 will always be something we sum over. That's the gauge field on the brane The other two fields in the story are bulk fields. So for those, we have a choice of boundary conditions to make the system well-defined. And as you can probably imagine, we can indeed find two possible scenarios that correspond, one to the invertible, the other to the non-invertible. Essentially, the mechanism involved relates is due to B1, whether or not we sum over B1, we are effectively changing the dressing. In that, if we do sum over B1, we have a total abelian TFT that is described in this matrix notation, if you wish. But that's a trivial dressing because it's like a Digraph-Witten theory of Z1. And therefore, this side of the story is the invertible side. Whereas if we do not sum over B1, then there is simply U1 at level M, clearly far from being a trivial topological dressing, and precisely the same dressing that we see in field theory. So this would be the non-invertible side. So it's very rewarding to see that the D-brane physics gives us the dressing for free, and it gives us also the same idea we saw earlier, namely that the same object in the bulk, depending on the boundary conditions, can either be become the invertible or the non-invertible symmetry generator. And now we can discuss, though, more. In particular, we can consider some of the physics of these non-invertible defects. And the first thing we can tackle is fusion. So fusion in this context would mean fusion of the non-invertible defect with itself has to do with a stack now of 2d5s, again wrapped on the S3. Now, naively, since we now have a stack of branes, we expect a non-abelian theory emerging on the word volume. And this is a little bit of a puzzle because we know that on the field theory side, we have abelian TFTs. Those are the ones that dress the defects. So how is this tension or puzzle solved? The resolution lies in the Myers effect. What happens is that even though we have a stack of 2 D5s, the configuration that minimizes the energy is actually a single D7, except that the D7 now wraps the additional 2 sphere we have in the game. So in other words, it wraps the entire T11, and it supports word volume flux for the little dA gauge field. In this instance, this effect is triggered because we have a B2 field on the S2. So that's sort of what makes it work. And one way to think about it is that in the word volume theory of the D5, there are 3 scalars. Now we have a stack, so they become matrices. And because of the B field, they acquire a non-commuting profile. And that's the same as saying that the D5 puffs up into a D7, but a D7 that carries D5 charge because it has word volume flux. So it means that what we have to consider is not quite the topological couplings on a stack of 2 D5s, but rather the topological couplings on this single D7 with flux. This can be done, again, starting from the best Zumino couplings, and we find this abelian TFT. So as we can see, we find 2 C3, so that's the naive symmetry generator. When we fuse it, the naive group-like parts just fuse in the naive way, and then the dressing turns out to be given by this abelian TFT, and we have verified that this is indeed can also be obtained from the U1 times U1 that we have in field theory. So in other words, the Myers effect explains why we have an abelian TFT in the dressing procedure, and also gives us a result that fits with the field theory fusion rules. And the final piece of information I would like to convey is that there is another stringy effect. This time is going to be a Hanani-Witten move that has an analog in field theory that has to do with the non-invertibles. To see that, I have to remind remind you of the fact that in field theory, we are considering the PSU theory if we want non-invertible. And that has a magnetic one-form symmetry, and the charged object under those are Toft lines. I'm going to denote them by H. So what we can do now is see what happens. How do the non-invertible act on the Toft line? And this is tested by letting one of these non-invertible defects move through an H line. And what happens is that a surface is actually generated in the process, in the move. And what I would like to claim in this slide and the next is that this is actually precisely captured in string theory by Hanani-Whitman transition. In this instance, it's about D3s and D5s. So this is very schematic. I'm suppressing various directions of space. But the idea is that when you try to move these branes past each other so that they cross, a new object is created that connects them. In this case, it's an F1. And so as we can see, this is precisely analogous to the phenomenon we see in field theory. And we can be a little bit more precise. We just have to identify clearly the stringy origin of all the pieces we have in the game. So what is the Toft line? So this is similar to what we have seen in n=4, is slightly more complicated because here what we have to consider is a D3 with flux. This is a slight technical complication. It doesn't change the main physics, namely that the Toft line is realized by a brane that is indeed extended along the radial direction. Whereas, as we have seen, the D5s, that eventually become the non-invertible defects, are at a fixed point. So it turns out indeed that given this configuration of branes, there is a well-defined notion of linking number between them, which we can measure either from the point of view of the D5 or equivalently from the point of view of the D3. That's a completely symmetric situation. Now, naively, if we were to move these branes across each other, L would jump. But that's not allowed because it's a conserved quantity. And the resolution of the puzzle, exactly as in the original Hanani-Whitman discussion, is that a new object with the appropriate charges is created as these two are passed through each other. In this instance, it's an F1, as in this brane diagram. And indeed, therefore, this demonstrates how the stringy dynamics of branes neatly reproduces this non-invertible action in the field theory. And indeed, so I think that's another interesting aspect of how the stringy side of the story can reproduce this quite non-trivial feature. And this is also the last thing I would like to discuss in detail today. So that brings me to my conclusions. So to summarize, we have seen how in holography, we can extract the topological couplings in the bulk, and this gives us access to the SymTFT. If we now take these topological couplings and perform a Hamiltonian analysis and Gauss law constraint analysis, this gives us a very systematic and streamlined way of getting our symmetry generators. And we have seen how the same object, depending on the boundary conditions, can account for both invertible as well as non-invertible symmetries. So that was the supergravity story. And then in the second half, we have seen how branes can be used to realize these symmetry generators. And in particular, we have seen how the physics of D-branes gives us the same TFT dressing that we see in the field theory construction in a very natural way. And we have also seen how some aspects of brane dynamics can actually reproduce properties of non-invertible defects, such as their fusion or how they act in some lines. This, in a sense, was just an example. We picked a concrete case study so that we can analyze everything carefully and establish a precise correspondence. But this also gives us several interesting directions for the future. You might have noticed that on the field theory introduction, I mentioned the fusion of the defect with itself that gave the condensation. But I didn't say what that means, what that looks like in string theory. It seems to be related to a process of tachyon condensation on a brane-anti-brane pair. But it's something that we would like to understand and study in greater detail in the future. More generally, I think it's quite interesting to try and see whether a brane perspective can tell us something new on the problem of how to think about the fusion in field theory, which sometimes is challenging. And more broadly, I think it's also quite important at this stage to identify more and more controlled examples. A few have already appeared in the literature in other instances, either holography or geometric engineering, but in a sense, there is much more to do. And finally, a bit more maybe mathematical and a bit more speculation. We know that ultimately in field theory, the language of category is really the best one to describe global symmetries, including the non-invertible ones. And on the other hand, we also know that the language of category appears naturally when we discuss branes in string theory. So this begs the question whether it is possible to establish a more precise correspondence between these two sides. I think that could be quite interesting to explore. And with that, I'm finished, and I thank you for your attention.
Thank you very much. Thank you, Federico. Very nice, great talk. Very nice result. And any question from the audience, please?
So one question I have, Federico, is in this example of Klebanov-Strassler and the non-invertible symmetry and so on, you can knew the answer from the field theory point of view. So did you also check that the other branes that you have in the in the bulk, they don't give anything weird? I mean, do they all fit with the symmetries that you would expect?
Yeah, no, there is nothing nothing weird sort of going on the other side. And also
yeah, so I guess my question is, why does it work? Like, is there why is it obvious that D-branes should become topological operators in the boundary? Was this is there? I mean, I guess it's clear that they become topological because you're dropping the DVI. But is there some more intuition for why they should be mapped to topological operators and global symmetries in the boundary theory?
Let's see. One way to think about it could be as follows. Like, we know that if we don't think about the branes, but we just think about the supergravity fields, I thought to consider holonomies of some p-form field. In this instance was the C3 field. So a holonomy of C3 that does not extend along the radial direction, that's the object that we know will become the symmetry generator. So in a sense, the problem becomes, can we, if you wish, think of an upgraded version of that holonomy, so to say. So the holonomy of C3, it's, if you wish, an effective description where we ignore all that's going on in string theory and just focus on the p-form fields we see in the topological couplings. But what is that in the full string theory? And in that sense, the D5 proposal seems to be the most natural one, because the D-branes are precisely the objects whose word volume effective action contains these holonomies of the bulk fields. That's just the electric coupling of the brane to its own potential of the matching dimension. So to me, that's one way to see how, in a sense, it's quite natural for these two things to be related. And the bonus is that once that holonomy becomes a full object in string theory, so say a D-brane, then it comes with all sorts of other ingredients for free in a very natural way. And most notably, the U1 gauge field on the brane. In field theory, we always have to somehow introduce by hand, if you wish, these auxiliary fields on the defect. And I find it quite remarkable that in the string theory picture, it's just there. It's just a property of the D-brane.
Okay. Okay.
Thank you.
Any other question, comments? Feel free, please. Okay, if not, we should thank Federico again. Thank you. Thanks again.